Imagine, it's deep night in a tropical forest. A cockroach scuttles across a damp log, antennae twitching, completely unaware. Somewhere in the shadows, something is watching. Something soft, something slow. The cockroach pauses. And then, in less time than it takes you to blink a fraction of a second, twin jets of glue erupt from the darkness, pinning it to the wood like a fly in amber. It struggles. It only makes things worse. From the gloom, a strange, velvety creature with dozens of stubby legs begins to amble forward, in absolutely no hurry at all. Because dinner isn't going anywhere. What you just witnessed is one of the most bizarre hunting strategies in the entire animal kingdom. And the hunter? Most people have never even heard of it. Welcome to Science Curiosity Scientists. Call their phylum Onychophora, which translates to claw bearers, because every single one of their many, many legs ends in a pair of tiny claws. The worm is soft, plump, almost cartoonish. They come in shades of blue, green, orange, pink, brown, sometimes patterned, sometimes solid, with colors varying not just between species but within them, possibly as camouflage against the forest floor. Some are barely the length of a fingernail, just 10 millimeters. Others stretch out longer than your hand, monsters of more than 20 centimeters. They have between 13 and 43 pairs of stubby legs, called lobopods, a pair of sensitive antennae on the head, and small, simple eyes. And they're so beloved, so charismatic in a strange prehistoric way, that several countries, Australia, New Zealand, and Brazil, have actually established dedicated conservation reserves just for them. Think about that. Nature reserves. For worms. Now, here's where your brain probably wants to fill in the blanks. You see a creature with lots of legs and claws, and you think, okay, it's basically a weird insect, right? Maybe a centipede's distant cousin. It must scurry around, chase down prey with all those legs, overpower it with sheer numbers of grabby little feet. That's the intuitive answer. And it is completely, almost laughably, wrong, because velvet worms have no exoskeleton. None. Unlike insects, spiders, and centipedes, the arthropods, velvet worms are soft, squishy. Their legs don't even have joints, because without a hard shell, there's nothing to bend against. And the consequence of that anatomy is that they are slow, painfully, almost meditatively slow. A velvet worm could not chase down a cockroach if its life depended on it. It could not pounce. It could not grapple. By the time it ambled over to a fleeing insect, the insect would have raised a family and moved to the suburbs. So how on earth does a slow, soft, defenseless creature manage to be a fearsome carnivore one that eats animals far quicker and better armored than itself? The answer is one of nature's most extraordinary weapons. On either side of the velvet worm's head, just beneath those delicate antennae, sit two prominent bumps called slime papillae. These aren't decorative. They are the nozzles of two enormous internal glands, biological fire hoses, loaded with a pressurized cocktail of sticky proteins. The hunt unfolds like this. The velvet worm emerges at night and patrols its damp, leafy domain with patient, deliberate steps. Its antennae sweep the air. Its skin reads the faintest tremor on the forest floor. Then contact. The brush of a cricket's leg. The flick of a beetle's feeler. The velvet worm pauses, investigates, considers, and then, if it decides this is prey, it rears its head and fires. In a fraction of a second, twin jets of liquid glue rocket out of those papillae, oscillating wildly through the air in a chaotic, zigzagging spray that drapes the victim in a net of sticky threads. The glue sets on contact with anything it touches, anything except velvet worm skin itself. The prey is instantly immobilized. And here's the cruel genius of it. The more the victim struggles, the more entangled it becomes. Resistance literally tightens the trap. Now, finally, the velvet worm takes its sweet time. It strolls over to its prisoner, opens a mouth lined with sickle-shaped jaws, injects strong digestive enzymes, and uses a sucking pharynx to slurp up its liquefied meal. And in a final flourish of efficiency that would make any frugal grandparent proud, it often eats its own glue back, recycling the proteins for next time. But here's the twist that has scientists in laboratories around the world amazed. That glue, it shouldn't work the way it does. Most biological materials we admire for their strength, spider silk being the classic example, owe their toughness to highly ordered, tightly structured proteins arranged like microscopic architecture. Velvet worm slime is the opposite. Its proteins are what biologists call natively disordered floppy, shapeless, chaotic molecular noodles with no fixed structure at all. And yet, when it leaves the body, that disordered slime forms a gel. The gel dries. The slime contains chemical components found in no other animal. Nowhere else. Just these strange, ancient, slow-moving creatures. And here, I think, is the real lesson hiding inside this strange little animal. Velvet worms cannot retain water, so they cling to the damp corners of the world, rotting logs, leaf litter, the deep soil of tropical and temperate forests, the occasional moist cave. They are split into two families, the Peripatidae and the Peripatopsidae, scattered across South America, the Caribbean, West Africa, Southeast Asia, Australia, New Zealand, South Africa, and Chile. So the next time you're walking through a damp forest and you turn over a rotting log, pause for a moment and look closely. If this strange little survivor blew your mind, hit that subscribe button. Have you ever seen a velvet worm in real life? Drop a comment below. I'd genuinely love to know where you spotted one. See you in next video with more interesting topic.